Hello everyone, this is a video about phase equilibrium. In this video, we are going to study what is phase rule, what is degree of freedom, what are eutectic systems, and what is a cooling curve. So let's start. What is a phase? Any homogeneous part of a system having all physical and chemical properties same throughout is called a phase. Consider three containers containing water, and ice, and water, ice, and water vapor. So in the first container, there is only one phase present, that is the liquid phase. Hence, P is equal to 1. In the second container, there are two phases, solid and liquid. Hence, there are two phases present. In the third container, there is water, ice, and water vapor. Hence, there are three phases. A system containing similar phases or only a one phase is called a homogeneous system, and a system containing two or more phases is called a heterogeneous system. We will look into some examples so that the term phase is more clear to us. Consider a case of pure substance. A pure substance is always made up of one chemical species, hence it is always considered as a single phase. Then we will consider a case of mixture of gases. Two gases always mix freely to form a homogeneous system. Hence, mixture of gases is always considered as a single phase. Two miscible liquids. Consider a case of ethanol and water. They are two miscible liquids that forms a uniform solution. Hence, two miscible liquids always forms a one-phase system. Consider a case of two non-miscible liquids. A mixture of two non-miscible liquids on standing forms two separate layers. Hence, a mixture of chloroform and water forms a two-phase system. Mixture of solid. By definition, a phase must have throughout the same physical and chemical properties. Ordinary sulfur, as it occurs in nature, is a mixture of monoclinic sulfur as well as rhomic sulfur. These allotropes of sulfur consist of a same chemical species but different physical properties. Thus, mixture of two allotropes of sulfur is a two-phase system. Components. It is defined as the least number of independent chemical constituents in terms of which the composition of every phase can be expressed by means of a chemical equation. Now we will take some examples so that the term component is more clear to us. Consider a water system. A water system consists of ice, water, and water vapor. It have three phases, that is solid, liquid, and gas. The composition of all the three phases is expressed in terms of one chemical individual, that is H2O. Hence, the water system has only one component. Consider a sulfur system. A sulfur has four phases, the rhombic sulfur, the monoclinic sulfur, the liquid sulfur, and the sulfur vapor. It has 4 phases, but all the 4 phases can be expressed by one chemical individual, that is sulfur. Hence, it has only one component, and the sulfur system is a one component system. Now we'll study about mixture of gases. Suppose there are two gases, oxygen and nitrogen, which are mixed to form a homogeneous system of one phase. Hence, there is only one phase, the gaseous phase, and the components are X of O2 and Y of N2, where X and Y are the mole fraction of each components. Hence, one phase can be represented by two chemical components, the oxygen and the nitrogen. Hence, a mixture of two gases is always a two-component system. Degree of freedom. It is defined as the least number of variables which must be specified so that the remaining variables are fixed automatically and the system is completely defined. For degree of freedom, when a system has a degree of freedom f is equal to 0, the system is known as non-variant. When degree of freedom is 1, the system is called univariant. When a system has f is equal to 2, the system is known as bivariant. Now we will have a look on various cases having various degree of freedom. Consider a case of a pure gas. For a pure gas, the equation PV is equal to nRT whole squared. Hence, if we fix the value of pressure and temperature, the volume will have only one definite value, or in other words, if we specify the value of pressure and temperature, the value of volume is fixed automatically. Hence, we need to specify two variables in order to completely define the system. So, for a pure gas, degree of freedom is 2. Now, we'll have a case of a mixture of gases. A system containing a mixture of two or more gases is completely defined when its composition, temperature, and pressure is specified. If pressure and temperature are only specified, the third variable, that is composition, can be varied independently. Since it is necessary to specify these three variables, hence a mixture of two or more gases has a degree of freedom F is equal to 3. For equilibrium between two phases, when there is equilibrium between two phases, there are two variables, temperature and pressure. If we vary temperature, pressure is fixed automatically, or if we vary pressure, temperature is fixed automatically. Hence, the system of equilibrium between two phases has a degree of freedom F is equal to 1. For a system in which three phases are in equilibrium, consider a case of a system in which ice is in equilibrium with water is in equilibrium with water vapor. The three phases coexist at the freezing point of water. Since the freezing temperature of water has a fixed value, the vapor pressure of water has also a definite value. The two variables, temperature and pressure, are predefined. Hence, the system is completely defined automatically. Hence, no other variables need to be specified. Hence, it has a degree of freedom F is equal to 0. This point is called the triple point, where the three phases water, water vapor and ice coexist at equilibrium. At triple point, degree of freedom is 0 or the system is invariant. The relationship between degree of freedom and number of components and number of phases was first given by William Gibbs in 1874, and it is known as the Gibbs phase rule. It says that the degree of freedom F is equal to number of components C minus number of phases P plus 2. So let's see the derivation of this phase rule. So F is the degree of freedom and it is called the number of independent variables. So number of independent variables is equal to number of variables minus number of relations. So for number of variables, there must be two intensive variables present to specify a system, that is temperature and pressure. These counts to 2. We can specify composition of a phase by giving the mole fraction of C minus 1 phases. Since there are P phases present, total number of variables are P into C minus 1 plus 2. For number of relations, the condition for equilibrium is that mu of a phase alpha is equal to mu of a phase beta is equal to mu of a phase gamma dot mu of P phases, where mu is the chemical potential of a substance. So there are P minus 1 equation. For each component there are total C into P minus 1 equations. Hence the degree of freedom F is equal to P into C minus 1 plus 2, that is number of variables, minus C into P minus 1, that is number of relation. On solving the equation, we get that F is equal to number of components C minus number of phases P plus 2. This is called the phase rule. Now we'll study about eutectic system. A eutectic system is a homogeneous mixture of substances that melts or solidifies at a single temperature that is lower than the melting point of either of the constituents. Now we'll study about the eutectic system of lead and silver. The three variables that need to be defined in order to specify the whole system are temperature, pressure, and the composition of the two substances. We will apply the reduced phase rule in order to see the variation of temperature with composition. Hence, we will take pressure as constant. According to reduced phase rule, the degree of freedom at any point is F is equal to 2. Hence, the system is bivariant. So, let's see the graph. This is a graph which shows the variation of temperature with composition. The things we can figure out from the graph are: the first thing, the melting point of pure lead is 327 degrees Celsius. The melting point of pure silver is 961 degrees Celsius. The eutectic point at which the both substances melt is 303 degrees Celsius, and the composition at the eutectic point is 97.4% lead and 2.6% silver. The degree of freedom along the OA and OB curve are 1, because when we fix the temperature, there can be only one composition value, and vice versa. This is all about the eutectic system and its variation of temperature with composition. Thank you. Cooling curve. A cooling curve is a line graph that represents the change of phase of matter, typically from a gas to a solid or liquid to a solid. The dependent variable is time and the dependent variable is temperature. So here is the graph. We have temperature on y-axis and time on the x-axis. First, the substance is cooled and the temperature drops rapidly. Then it comes to a thermal arrest and stays at that temperature for some time. At this temperature, the liquid phase and the solid phase are in equilibrium. When all the liquids are converted into solids, then the temperature falls rapidly again. This variation of temperature with time is known as the cooling curve. For notes of these topics, kindly leave a comment below and I'll reply to all of them. Thank you for watching this video. Do like, do subscribe for more chemistry related content. Thank you.